Okay, so now we're going to look at a specific type of distribution. We've been talking about probability distributions in general, but many times we can identify probability experiments that have a certain type of distribution. And when an experiment consists of a fixed number of independent trials, each of which has two possible outcomes, where the probability of a success remains the same on each trial, then the random variable that represents the number of successes follows what is called a binomial distribution. So we're defining here a set of circumstances under which we have something called a binomial distribution. And when we know that it follows a certain distribution, when we know it follows a binomial, then we're going to come up with formulas and different techniques for being able to find those probabilities easily and to be able to find the mean and the variance of those things pretty easily. Okay, so let's just kind of think about this. Here are our conditions for a binomial experiment. There's a fixed number of n trials are conducted. There are two outcomes for each trial. One we're going to label as a success and one we'll label as a failure. The probability of success, which we'll call P, remains the same on each trial. The trials are independent of each other. And the random variable y that we're interested in here represents the number of successes that occur in those n trials. Now, I always think about a binomial experiment as something that is analogous to flipping a coin, although it may be a coin that's not fair, one that's weighted one way or another. And so suppose that you want to count up the number of heads there are in the toss of n coins. Then the trials are independent of each other. One flip doesn't affect the outcome of the next flip or any other flip. The probability of a success remains the same. If it's a fair coin, then that would be 0.5 on each flip. If it's a weighted coin, it may not be 0.5, but it would stay the same from one trial to the next. There are two outcomes, a success or a failure, and those labels really don't mean anything. I mean, getting ahead may be a success or it may be a failure. It's just a matter of what you label it. So we're going to call the thing that we're trying to count up our successes, even if it's not really what we're wanting. And there are n of these trials that are being conducted. And so if we can take whatever situation we're dealing with and sort of say this is analogous to the idea of flipping a coin, then chances are we're talking about a binomial experiment. Okay, so let's do a real brief review of combinations here. You should have seen this at some point, but the number of ways that R objects can be chosen from n is given by n choose R. That's how this is read, n choose R, or the combination of n objects taken R at a time. Okay, and this is equal to n factorial over R factorial times n minus R factorial. So let's look at an example. A box of LED light bulbs contains 8 good bulbs and 2 burned out bulbs. 4 bulbs will be selected at random to put into a new lamp. What is the probability that all 4 bulbs are good? Okay, so let's see. We have 10 bulbs altogether. 8 are good, 2 are burned out, and we're going to be selecting 4 of those. Let's write some of this down. So there are 10 bulbs, 8 are good, and we're choosing 4. So I think it's probably worth thinking here about our sample space. Our sample space would be that we're choosing 4 bulbs from 10 altogether. So we want to think about the number of ways in which we can do that. Well, the number of ways to choose 4 from 10 good bulbs, or from 10 bulbs altogether, well, that would just be 10 choose 4. That's our sample space. That's the number of ways in which we can do that. So what about the number of ways to choose 4 good bulbs? Well, there are only 8 bulbs that are good. And so the number of ways in which we can choose that would be 8 choose 4. So to find the probability of choosing 4 good bulbs when we make our choices here would be the number of ways to get 4 bulbs out of the 8 that are there over the number of ways of choosing 4 from 10 altogether. So that would be 8 choose 4 over 10 choose 4. Now there are different ways we could go about doing this. We might be able to put this right in the calculator. The calculator has a key, or has a command that allows you to go in and do combinations. It's under the math menu and the probability menu here. So we could just do something like 10 and then put in 10, then hit this command, and then put in 4, and that would give us this value up here that we were looking for. So that's one way we could do it, but I don't think we need the calculator in this case. This is entirely doable. Because remember here that 8 choose 4 is 8 factorial over 4 factorial over 8 minus 4 factorial. Okay. And so that's going to be over 10 factorial over 4 factorial times 10 minus 4 factorial, which is 6 factorial. Okay, so we've got this calculation we're trying to do. And if we remember what about factorials here, this would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, that's what this 8 factorial is. So that would be 8 times 7 times 6 times 5. But anything beyond that would just be 4 factorial, which is going to cancel with one of these down here. So that is over 4 factorial. I've canceled one of them out because that's just going to be the 4 times 3 times 2 times 1 that's up there in the numerator. And down here in the denominator of this thing, and yes, I could probably do some more simplification here, but let's just move on here for a second. This is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, if I do 10 times 9 times 8 times 7, anything I write beyond here is just going to be 6 factorial, which will cancel with this 6 factorial that's down here in the denominator. So that is gone. That 6 factorial is canceling out, and I'm left with nothing but this 4 factorial right here. And it should be obvious that at this point, those 4 factorials will just cancel out. You can just say they canceled out, or you could do it, you could say, hey, what if we multiply this big fraction by 4 factorial over 4 factorial? You can see that those things just cancel each other out. And so we're left with 8 times 7 times 6 times 5 in the numerator. And in the denominator, we're left with 10 times 9 times 8 times 7. And it should be obvious right away that the 8 times 7 cancels with the 8 times 7 down here. And we could probably do some more canceling here, but it's probably fine. Just go ahead and multiply these things out at this point. 6 times 5 is 30. 10 times 9 is 90. Looks like our probability comes down to 1/3. Okay, so let's think about our binomial probability distribution. For a binomial random variable y that represents the number of successes in n trials with success probability p. Notice here that we are given n and p. Those are what we call the parameters of the distribution, and you have to know those really to be able to move forward to find any probabilities. Then the probability of obtaining y successes is p of y equals n choose y times p to the y times 1 minus p to the n minus y. And here y goes from 0 all the way up through n. Remember, y represents the number of successes in n trials here, which is why y can be 0. There may be no successes. There may be one success, there may be two successes, or there may be all the way up through n successes. Okay, so let's think about this formula for just a moment. And I'm going to go back and refer to an example that we've done in a previous lecture. We want to think about the idea of flipping a coin 3 times, and what we are interested in is the number of heads that we get. So let's go over to Excel, and I'm just going to come up with my sample space here. And we've done this a couple of times here. So I could get a head or a tail on the last flip. The second flip could have been a head or it could have been a tail. And so if I copy these, I can see that this represents pretty much all of the possibilities for the last 2 flips. But if these are all the possibilities for the last 2 flips, the first flip could have been a head for any of these things. And I could have had any of these possibilities for the last 2 flips where I have a tail for the first flip. So essentially what I've done here is I've come up with a sample space for looking at the number of, or the outcomes when I toss a coin 3 times. Suppose that what we're interested in here is we're going to count up the number of heads that we get. And in particular, let's think about something like this. Let's think about the probability of 2 heads. We get exactly 2 heads. Okay, so if I'm going to do that, I can see that that happens like right here. This is an outcome that has 2 heads. And let's think about the probability of when we actually flip each one of those different coins. How do we get that? We get that the probability of this outcome happening would be the probability of getting a tails on the first flip, which is 0.5, and getting a heads, which is 0.5, and then getting another heads, which is 0.5. Now we're assuming that we've got a fair coin here. It could be that we have an unfair coin. It could be that the probability of getting a tails on any given flip is, let's say it's a weighted coin. Say that's something like 0.4, and that the probability of getting heads on any given flip is 0.6. All right, just for the sake of argument here, let's suppose that we've got an unweighted coin. Then when we're looking at this outcome here, the probability of this outcome happening would be 0.4 times 0.6 times 0.6. Notice here that in another case, like this one right here, this outcome, that probability would be the same, right? 0.6 for the first one, 0.4 for the second one, 0.6 for the third one. And here's another one where I have 2 heads. 0.6 times 0.6 times 0.4. So in either of those cases, when I look at these outcomes individually, I'm getting 0.6 times 0.6 times 0.4. Now, if we go back and look at this, we can see that that is actually kind of what's happening in this last part of this formula. Whatever the probability of a success is, in our case it was getting heads, we get that, and that's raised to the y. We were looking for two successes in this case, so we took 0.6 and we squared it. Whereas this part over here would be the probability of getting a tails, which is 1 minus 0.6, which is our 0.4, and then we get n minus y. Right, that's the number of flips that were left. So that would be just once in our example. So that's kind of taking care of this part of the formula. But where does this part over here come from? Why are we multiplying that by some number out here in front? Well, if we go back over here and look at this, we can see that there are 3 different ways in which we can get 2 heads. We can get 2 heads here in this outcome. We can get 2 heads here in this outcome, or we can get 2 heads here in this outcome. So when we multiply that 0.6 times 0.6 times 0.4 to get any one of those outcomes, what we're really doing is we're finding the probability of getting 2 heads here, or here, or here. We're taking the union of 3 different events. And what we would do is we would add those 3 probabilities, which is the same as multiplying by 3. That number 3 is really what this part of the formula is doing over here. And so we've got our binomial probability distribution, and we've got a formula that calculates these things for us. Now, there are also other ways of doing this. We have technology, and I'll show you some of that when we get into looking at an example. Now, when we're talking about a binomial distribution, if we know it's a binomial random variable and it meets all of the conditions for it, then often we will denote that this way. Y follows a binomial distribution, and the parameters are n and p. So let's look at an example then. A large shipment comes with a guarantee that it contains no more than 15% of defective items. If the proportion of items in the shipment is greater than 15%, the shipment may be returned. You draw a random sample of 10 items and test each one to determine whether it is defective. Assume that in fact 15% of the items are defective. We want to know what is the probability that 2 of the items tested are defective. Okay, so I'm going to go over here and just summarize what I know. I know that we are taking a sample of 10 items and we're going to test them. And we're told that there's a 15% or 15% chance that any one of those items are defective. So it seems to me like we're told then that y is binomial, where n is equal to 10, and our probability of success is 0.15. So we know this. And what we're trying to find in part A is we just want the probability that would be 2, the probability of 2, that 2 of those items are defective. Now we've got a formula for that. We've got a formula that tells us how to find that probability. We know that this is going to be 10 choose 2 times 0.15 raised to my y value, which is 2, times, now what I've got here is got 1 minus p, so that would be 0.185. And 2 goes here out of 10, so this is going to be just the rest of them, so this is going to be 8. And we can go in here and we can calculate this. Okay, so I'm going to just do this on the calculator here. I'm going to go in and see what this turns out to be, just by sort of doing this in the calculator. So I want to do 10, see, math, go over to the probability menu, and select the combination 2. Okay, so that's my combination 10 choose 2. And that's being multiplied times 0.15 raised to the second power. I guess I could just do a square there. And that's being multiplied times 0.85 raised to the 8th power. And I see that turns out to be something like 0.2759. Probabilities are almost always rounded to 4 decimal places. Okay, so that wasn't too tough to do that. The calculator has a command that's built into it, though, that does these types of probabilities. If I go to the distributions menu, that's second, Vars, takes me to the distributions menu, and scroll all the way down until I see the binom PDF. Now the PDF here stands for probability distribution function. And probability distribution functions are generally used when we're trying to find exact probabilities. That y is exactly equal to this number of successes. As opposed to the CDF, which we'll see what this does here in a minute. But what I do is I put in my n, comma, p, comma, and then the number of successes here. So my n in this problem is 10. My probability of a success in this case is 0.15, and I was looking for the probability of exactly 2 successes, and so that's going to be 2. And I see that I get my probability there. Now I can also do this in Excel. Let's go over here to Excel. Okay, so I know that this is binomial with n is 10 and that p is 0.15. So I'm just putting in my parameters. I'm going to count up my number of successes. I'll call those y. So y could be 0, could be 1, could be 2, could be 3, and so forth. Okay. Okay, so what I want to find is I want to find p of y. So this is my command I'm going to use. It's equal binom dot dist. Okay, so it's going to ask me for several things here. It's going to ask me for the number of successes, the number of trials, the trial probability, and then there's this fourth command, which is fourth option, which is the cumulative, and that's a true or false statement there. So the number of successes, well, that's the thing I'm trying to find. That is what is over here in A5. Okay, so A5, that's what's in that column. That was my 0. It's hidden right now, but that's what it is. Okay. The number of trials, well, that's this value up here. And I'm going to put some absolute reference qualifiers around that. The probability success, that's going to be this number right up here in B2. And I'm also going to put the absolute reference around that because those values won't change. And now I've got the cumulative. Now what it's asking for here is whether I want to do this just looking at that one value that I put in for my successes, or whether I want to find the probability of everything up to and including that, whether I want that to be cumulative. Well, in this case, I just want it to be that one value. So I'm going to put in false here and press enter. So what this is doing is it is looking at the value over here in A5, it's looking at the value of n and p, and it's calculating the binomial probability for that. And I'm going to copy that all the way down. Okay, so remember here that y can actually go anywhere from 0 to 10. And if I scroll down here, I can actually go ahead and just fill these in. Okay, and I'm going to fill in all these different values. So I've got a column here that tells me all my probabilities going from 0 down to 10. Now remember, we were looking for this one just a few moments ago. We were looking for the probability of exactly 2 successes, and we found that that was 0.2759, and we can see that that's exactly what Excel is calculating here. But we've actually got more information. We've got all of these probabilities for any of the outcomes from 0 down to 10. And notice, think about what would happen here if I were to sum up all of these probabilities. Remember, what should happen is that if I sum all of these things up, that should represent everything. If it's a valid probability distribution, then that should give us 1. Okay, so let's look at some more of these probabilities. What is the probability that fewer than half of the 10 items tested are defective? So we want fewer than 10. So in part B, fewer than 10. So that means that we would want y to be less than, I'm sorry, what was that? Fewer than half, I'm sorry, fewer than half. So that would be, want y to be less than 5. Fewer than half. 5 of them would be half, and so we want y to be less than 5. Now, that means that we could do this. We could find p of 0 plus p of 1 plus p of 2 plus p of 3 plus p of 4 plus p of 5. Oh, that's not, no, we're not going to include the 5. They'll just go up through p of 4. We could find each one of these probabilities using this same way that we did right up here. And, you know, doing this by hand would be pretty tedious, you know, especially if we're going to be trying to find these combinations and just do it. Even if we're using the calculator, that would be pretty tedious. So what we might want to do is we might want to think about this in terms of what's called a cumulative distribution function. A cumulative distribution function means that, that we are looking for probabilities in the form y is less than or equal to some value right here. And what we'll do is we will call this capital F of y. Okay, so we can see that here in part B, less than half, less than 5, this would be the same thing as capital F of 4. Right? Because less than or equal to 5, less than 5 is the same thing as less than or equal to 4. So we could do this using the cumulative distribution function and putting a 4 in there. Now your calculator has this built into it. If we go back to the distributions function and I do the binom CDF, that's cumulative distribution function, then I do this the same way. 10, 0.15, 4 is what I'm going to put in. And we see that that probability is 0.9901. If we're doing this using something like Excel, well then this actually becomes a little bit easier. Less than half means 4 or less. That means I'm just going to sum the values of these right here that are highlighted. And so I could do that using a pretty easy Excel command. Sum these values right here going down through 4. And we've got that probability. What if we want to find the probability that 7 or more of the items tested are defective? Well, again, we can use some of the same tools that we've been seeing here. Probably the easiest one is to use something like Excel. 7 or more. That means that when I look at my list over here, I want the probability of 7 or more. So that would be the sum of these probabilities right here. That would just be the sum of these values here. Okay, so let's talk about expected value and variance. Let's let y be binomial with parameters n and p. Then the mean, mu, is equal to e of y, which is n times p, and the variance, sigma squared, is equal to n times p times 1 minus p, or n times p times q. Q here represents the probability of a failure, and that's just 1 minus p. Let's think about this for a moment then. Let's think about particularly where the mean comes from in this case. Suppose that we think about a random variable. I'm going to call it x. And actually this isn't just one random variable. It's a one in a series of random variables. So I'm going to call this x of I. And let's suppose that x of I is binomial, and we've only got one trial here. This is like one flip of a coin. So we're flipping a coin one time, and we're looking for the probability, or this number of, we're looking whether we get ahead or not. If we get ahead, x will be 1. If we don't get ahead, then x will be 0. And the probability of getting ahead will be p. Let's think about how this random variable would relate to the random variable that we're talking about here, which is a binomial where we flip a coin n times with a success probability p. So here we flip a coin n times, and we're looking for the number of heads that we get. Here we flip a coin one time, and if we get ahead, then that random variable is 1, otherwise it's 0. It seems like this random variable, where we're counting up the number of heads that we get, would be just doing this one over and over and over again and summing up the results. And that's exactly what turns out to be true. Y is the sum of these type of random variables. All right, and the I here goes from 1 to n. So what we're trying to do is we're trying to find the mean, and I'm going to put a little y here to denote that we're trying to find the mean of the random variable y, or if we want to call that the expectation of y. And we know that y here is the sum of these random variables where we're just flipping the coin a single time. I goes from 1 to n. And because we know that expectation is a linear operation, we can rewrite this. That means that this is the sum, as I goes from 1 to n, of the expectations of x of I. And so let's just think for a moment about the expectation of x of I. Let's think about what that would be. If we flip a coin a single time, we get a head, that random variable becomes a 1, otherwise it becomes a 0. Over time, with a success probability of p, we would expect that the proportion of heads would be p. And that's exactly what turns out to be the case. This expectation just turns out to be p. And so what we have here is we are summing from 1 to n just the constant p. And so this is just p times p, p plus p plus p plus p, and we keep on doing it n times, which is where we get the formula n times p. So the mean is n times p. Now the variance is a little bit harder to prove, but a similar trick is used to find the variance here in this case. So let's look at an example. The Agency for Healthcare Research and Quality reported that 53% of people who had coronary bypass surgery in a recent year were over the age of 65. 15 coronary bypass patients were sampled. What is the mean number of people over the age 65 in a sample of 15 coronary bypass patients? And what is the variance of the number of people over the age 65 in a sample of 15 coronary bypass patients? So here, we know that we've got a binomial random variable, and we're told that n, the number of trials here, is 15. The success probability, or at least what we're calling a success in this case, is 0.53. And we're asked to find the mean and the variance. Well, the mean is equal to n times p, which is 15 times 0.53. We multiply this out and we get 7.95. The variance will be n times p times q. Remember here, q is just the probability of a failure. So that is 15 times 0.53. Q is just 1 minus p, so that's going to be 0.47. And what we get here is we get 3.7365.